What's going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Today we're doing a review lab. We're going to look at some motion and think about some review concepts. It's a lab we've done before. It's similar. We're going to use a different object than normal. And then we're going to test a student's theory. A student has a theory about energy. I'm going to give that a test, okay? So it's our review lab. Here's essentially what's happening, okay? We're going to have an object. This is going to be a hollow cylinder, not a hoop, a hollow cylinder. And we're going to model that with a roll of masking tape here. We're going to roll it down a ramp and take some and kind of go over some review concepts of that, okay? So I can turn this thing around right here. You can see my ramp right here in front of us. So essentially all we're doing today is taking this hollow cylinder and rolling it down the ramp. That's all we're doing with it. So to review this kind of motion, let's go to the board. If we're going to review this motion, the first thing I want to do is talk about the forces that act on it. Here's the object. Its initial angular velocity is 0 radians per second. Again, we're in radians per second because it's a rotating object. That doesn't mean it's not moving linearly. Radians per second is just how we measure how quickly something is rotating down an incline as opposed to how it's moving linearly. As it rolls, right, there are some forces on it. Obviously, the force of gravity, which always acts straight down towards the center of the earth. That direction is never a question. There's a contact here between the surfaces, and that contact produces this normal force, or Fn. Normal force is the word normal. It's defined as a 90 degree or perpendicular. So normal forces are perpendicular to the surface. There's where the surfaces meet. There's a normal force pushing straight up from there. Now, this surface is not frictionless. If this surface were frictionless, this thing would be sliding down the incline, but it's not sliding, it's rolling, so there must be some friction. If there is friction, there's friction, static, and that's up the ramp. How do I know it's up the ramp? I know it's up the ramp because as this object begins to move from rest to rotating, it rotates in a clockwise fashion. I know there's friction because there's a normal force. So I know there's friction because of the fun equation, right? Force of friction is the result of coefficient of friction and normal force. If there's a normal force and a coefficient of friction, there's going to be friction. So I know there's friction, but I just need to figure out which direction is the friction, up the ramp or is it down the ramp? Well, if it is going to rotate this way and there is friction between the surfaces, that friction is the only force acting to produce a torque. My pivot is going to rotate around the center of the object. The only force acting away from the pivot or at an angle, a perpendicular angle to the object, is friction. Friction has to point up the ramp to produce that clockwise torque. The normal force won't produce the torque, and gravity won't produce the torque. The only force that will is friction, so it must be pointed up the ramp. So these are my forces. As it rolls down the ramp, this hollow cylinder will reach the bottom of the ramp, moving much faster, right? The final angular speed is going to be much greater than 0 radians per second. It's going to have a linear speed now. We can call that V. Final is going to be also greater than 0 meters per second. This motion is bridgeable because it's rolling and moving translationally as a result of each other. These are all kind of motions that we can be thinking about here. If I think about the graphs, I can have 6 graphs. I can be asked to graph position, velocity, and acceleration, all linearly. And I can be asked to graph theta, omega, and alpha over time. I can be asked to graph both my linear and my angular kinematics graphs. So where does it start? Let's call it top of the ramp 0. As it moves down the ramp, it speeds up. So it starts covering distance slowly and then increasingly covering distance. And my velocity starts at rest and slowly speeds up. And my acceleration is constant, driven by the parallel force of gravity down the ramp, resisted by the upward static friction force, but gravity pulls it down the ramp, and that force is constant. There's no changing force, so I see a constant acceleration. And I notice the same thing here. It rotates very slowly and then rotates much more quickly. It rotates from rest, so it starts slow and then gets to a higher and higher velocity. And same thing with my angular acceleration. The only torque causing force is force of friction, and that force of friction doesn't change because the surface doesn't change and the normal force doesn't change. These are my kinematics graphs. Notice they are pretty much identical left to right, linear and linear and rotational. They are pretty much the exact same. And that makes sense. That's why I can bridge them. Because their motions are so closely linked, the only difference is that radius term when I start doing the math. So this is a kind of a kinematic forces type review on this motion. Okay? If I wanted to write a net torque expression for this, I certainly could. I could certainly write my net torque, net force equations. Let's go ahead and do that. The only force that causes a torque here is the force of friction times the distance, the radius that acts at. And that will go ahead and cause an acceleration in terms of rotational inertia. And because this is a hollow cylinder, we end up with expanding this equation. We get force of friction static times the radius, and that radius is the big radius. We can call it R big or R outer. That's equal to I think for a hollow cylinder, I think it is 1/2 of R1 or R inside plus R outside. That whole thing squared times m, right, times alpha. Let me double check that because I don't want to lead you all astray. That's my memory says that, but also my memory is garbage, and you all know that if you've been in my classroom long enough. Let's see. The hollow cylinder, 1/2 m. That's where the square goes. The square goes here, not on the outside. It's here. Squared here, squared here. So we square those radii first, and then we're here. So this is my general net torque expression. Force of friction is acting at the larger radius, or we can call it the outside radius because that's what we call it over here. That equals the rotational inertia times its angular acceleration. And of course, we can replace angular acceleration with our linear acceleration. We also have an F net equation here. If I'm just thinking about ways I could model this motion, I could think about the F net, which is MA. The forces that act on it, we have Fg down the ramp minus force of friction static up the ramp. It's not equal to 0. This thing isn't at rest or in a constant velocity. It is speeding up. So I see that the acceleration, or MA, F net is equal to mg times sine theta, if theta is the angle of the ramp, minus the force of friction static. And so I have two equations, right? I've got one up here, and I have a second one down here. Both equations have force of friction in it. Both equations have acceleration in it. At times during this unit, I asked us to solve for linear acceleration or derive an expression for linear acceleration or what have you. And this is how we did it. We always would write a net torque for the rotating object. We'd write a net force for the rotating object, and then we'd go ahead and do some substitution. So how did we do that? This is how we did it. We took our model, we modeled it mathematically, and then we kind of isolated some variables and got down to some of the more basic physics variables and physics constants as we did that. So as we review this motion, we have graphs, we have models, and we have math, okay? Explanations might come later, but certainly our graphs and our maths are right here. Let's get into the lab portion of this. Let's get into the data collection and get into some a testing of a hypothesis, if you will. Okay, there's a student, for instance, or for example, a student proposes this. A student proposes that they can use energy to predict the speed of the tape roll of the hollow cylinder as it rolls down the ramp. And they propose this. They propose that the relationship between velocity and height is this. Now, where does this come from? We'd have to think back to Unit 4, or our energy unit. But basically what they're saying is that the object starts here and ends here. And because of that, there's UG up here. There's K down here. If we ignore the work by friction, because friction is static, it's not sliding, friction isn't stealing any energy. There's no thermal energy here because there's no sliding. So there's actually no distance covered by friction. So because of this, the student would say UG, energy initial, plus 0 work is equal to the kinetic energy final. This is something we would have said a long time ago. It's our energy work theorem. And so what they're basically saying is that mgh is equal to 1/2 mv squared. And from here, they derive this expression. And they said, okay, I can predict the speed at the bottom of the ramp, the final velocity. I can predict that through energy, or at least that's their hypothesis. We haven't done this yet, but that's their statement. And so we're going to test that here today. How are we going to test that? We're going to take some data. Here's the data we're going to take. We're going to take the data we need. We're going to need to know the distance down the ramp this thing travels. Obviously, we're going to need to know the height. We're going to have to calculate final speed. Final speed will come from the distance traveled and, of course, time. You're going to use distance over time to find final speed. And I know what you're thinking at home. You're like, Gustin, this thing's accelerating. No way can I use distance over time. Change in position over time equaling velocity is not an equation we like to use when things are accelerating. And my response to that is not so fast. We don't like using this equation, or we do use it sometimes incorrectly when we say this is the final speed of the object. And that's not true. This is not the final speed of the object. What is this? This is the average speed of the object. And that's where the hang-up comes from. We get so lost, like, oh, okay, fine. It's the average speed, not the final speed. This is okay to use as long as you understand what you're getting out of it. Now, how can I use average speed to find final speed? Remember, average speed is also equal to final velocity plus initial velocity over 2 when something experiences a constant acceleration. So right here, I'm able to figure this out. And we start from rest, so bang, there we go. But change in position over time is equal to final velocity over 2. You can find final speed down here. We can measure the height here. We'll need distance and time to get this side. Then we'll multiply it by 2 to get our final speed. Let's take some data. Make sure you have this kind of set up here so we can do this. I'm only going to measure this once, okay? There's a couple things I'm going to measure. I'm going to go ahead and measure the height of this. I'm going to back us up. Right now, let me crank up my chair so I can place my computer screen right here. There we go. Let's get the height or the length of this. I will drop it from the same length every single time. So we'll drop it from here, and it's going to roll 91 centimeters. I'm going to record that, but the distance it's going to roll is always 0.91 meters. 0.91 meters, we're going to go that way the whole time, okay? I'm not going to measure the height every time, but I will tell you the angle. So you'll need to go ahead and do some trig. If I tell you the angle and you know the length, you can easily use some trig to find the height, all right? Let's go ahead and start this thing down a little low. Start it down here. Angle is 4 degrees. 4 degrees. Let's make sure we write all of these down. 4 degrees is my first data point. I'm going to let it fly. You time it. Your job is to time this. So make sure you're not in times 2 speed or 1.5 speed. Go to normal speed during this section of the video. Ready? 3, 2, 1, go. That's it. That's done. That's done. Cranking it up. That was 4 degrees. Let's go up to, up to 8 degrees. 8 degrees. 3, 2, 1, go. At 8 degrees, there was your drop time. Go ahead and get it. Again, do not be in times 2 speed. I can't tell you how silly some of the data looks when students come to me and say, Gustin, I got terrible data because I was watching a time video or taking time data in times 2 speed. This is 13 degrees. 3, 2, 1, go. 13 degrees. Cranking it up. This is 17 degrees. 3, 2, 1, go. 17. We'll get 2 more of these data points, okay? $23 degrees. 3, 2, 1, go. 30 degrees. 3, 2, 1, go. There we go. 30 degrees is the last one. Hopefully, that's a pretty wide spread of data there. You've got, now you should have time. You're taking time. You should have distance. Distance stayed the same the whole time. In order to find height, you got to use a little trig. Final speed, you've got to use a little kinematics and average velocity. The last thing you should be asking me is, Gustin, wait, don't go yet. What was the radius for the inside and the radius for the outside of this hoop? What are they? I'll tell you what they are. The radius for the outside of the hoop is, let's call it 5.5 centimeters. 5.5 centimeters. That's not meters, that's centimeters. And the interior radius here is 4 centimeters. Not meters, 4 centimeters. Make sure you do your conversion. You might need that for an I value later. I don't know what you might need it for, but that's there for you. Again, the question. Student proposes this. This works. Your job. Use this data. Construct a graph to determine if that is a proper relationship between height and final velocity using energy concepts as this object rolls down the ramp. If you've got questions, drop in the comments. Send me an email. Ask me in class. Good luck on your summatives. Until next time, see ya.